Hi everyone. This should be our last installment for class today, February 5th. I wanted to get into a little more detail around utilization of R. We've done some work sort of introducing foundational concepts in the class, what we mean by data science, data types we could use, and some reasonable amount of work now getting up to speed in R. So I wanted to extend on that work and see how far we can get in this slide deck of data types, vectors, and subsetting, all things we're going to be doing in R. Okay, so this slide deck is in Moodle. Actually, everything that I've presented so far in the class is in Moodle, so you can go at your own pace through the slide deck or make notes or whatever you like. So, and once again, I'm on just to remind you, and also apologize in advance if you hear me coughing or whatnot. I'm doing this recording because of being just really sick. So, mostly not wanting to infect you guys with what I have, which I think was a good thing. Definitely would not want you guys to get sick. Okay, so let's get on with the material. We are thinking the way R is thinking, and R is set up from a statistician's perspective. So what that means is we have variables that are likely measurements. They may be a deliberate measurement as part of a scientific experiment, or these may be measurements that have just sort of happened, like computer monitoring or streaming information. But we've got some kind of measurements, and so think of those as variables. And here there's a nice definition: an ordered collection of measurements on a group of subjects. So subjects could be people, it could be something else, just whatever we're interested in studying. And these measurements are going to inform the type of analysis that we can carry out. So do we want to do things like compute a mean? Do we want to do things like other measurements? For example, if we had categorical variables, like for example, you might have information on whether your subjects are male or female, for example, and then in that case, computing a mean is kind of tough to do anyway because they're not numeric, but wouldn't even really make sense, right? So what representation of the measurements that we actually have determines the type of analysis that we can actually do. So understanding those representations are really important. Another thing to just always keep in mind as you're doing these analyses is missing data. It's quite a common occurrence. This is something that you will want to pay attention in any study that you're doing. And we have different remedies on ways to handle missing data. Is it systematic? Is it random? All of these things can impact the reliability of your output and how you actually work with the data during the experiment itself. Okay, so remember, R is working from a statistician's perspective. They have built in several data types in R to reflect that perspective. We are working with numeric, character, logical. There are some other data types that we're going to work with. But those are the ones we're going to start with. And if you use the function class, so I apologize here for this cap. That should be a small, just like the other ones. But if you're using the function class, it will tell you literally what class that particular object is. So you can think of it like a data type. So 3.5 is numeric. A series of letters is a string, so that comes out as character. And then I mentioned in the last recording how capital TRUE, like this, and capital FALSE, like false, those are special in R, and they represent the logicals, true and false, or 1 and 0, and so on. And you can see here that's actually, now we can actually see how it's actually a special class of itself. So that's the logical class. It just literally means a binary, true or false. Okay, factor is another class that we're interested in. We will do a little bit more digging into that one. Factor is a little bit special. Now, it goes to the fact that we're doing data science, the fact that we're working in R, and these types and the representations that are constructed in R are all around doing data science and doing stats. Which makes it, by the way, makes it different from any other computer language, pretty much. Okay, so all of these objects that we were just looking at on the previous slide are technically vectors in R. And a vector could be of length 1, so, or length 2, however long it wants to be. Vector is our sort of primary representation in R. Pretty much everything is a vector of some sort. And this is a good thing because it means that internally R can actually do some very fast computations across this vector representation of the information. Okay, so in these vectors, R always has an ordering on them. So here's an example. If you think of a vector of data, so in this case it would be weight data with these measurements here comprising the weights for the different subjects in the variable, they would implicitly be ordered by R. So position 1 and all the way through to however many positions there are. So notice for people who have some experience in programming where you start counting from 1, in R, we're not counting from 0. Again, we have that statistician data science perspective. We don't have necessarily a computer science perspective. We don't need to start counting from 0, for example, which just means you have to translate all the, just have to sort of bump everything up by 1 if that happens to be your background. Okay, so for every vector, you have the same type of element in there. These would all be numeric, or they would all be character, or they would all be logical, for example. So I'll put this family data set that is the example in this tutorial up right after I finish recording. So by the time you get this, it should be in there in Moodle, so you can actually try out these exercises as I'm going through the lecture if you like. So there's our example family data set has 14 subjects in it. There are data vectors on first names, age, gender, weight, actually the weight variable on the previous slide, height, and then there's a logical of whether or not they are considered obese or overweight. And that was defined by having a body mass index or a BMI of over 25. So then the question is, what are the data types of these different variables? Okay, let's take a look. So F names gives us our first names, Tom, May, da, da, da. Now notice that R is giving you hints here. So characters are represented with these quotes around them. So you sort of have a sense that they're character. And you can actually see, if we look at the class of this variable, it says it's character. Now, of course, they all have to be character in there. So this sort of mismatch in font here, there's no meaning to that. That's just a PowerPoint problem. So those should be the same double quotes. Age, so F age, you can see, like family age, you can see 7733 and so on. This is integer. So it's actually a little more precise than numeric. Numeric allows for the decimals. We can make a smaller vector here by storing them as integers, so R allows that. We have no decimal places here, so they're just stored as integer. Just a couple of things that might look confusing if you're new to R. So I mentioned in the last lecture that they are indexes with these square brackets, and on the last slide we saw that R has an implicit indexing for any vector. So that's what's coming through here. This square bracket 1 square bracket is saying Tom is the first entry. That's what it's saying. And then it goes 2, 3, 4, 5, 6, 7, 8. I apologize, the cell wrapped in R. It should be here. That's just from the PowerPoint. And then the 9th one is Tim. And so you can see that actually does correspond with the indexing. And so it says here's our 9th value of Tim. Now for R, it didn't see the cell wrapped. That's just like I said, a display mistake on my part here in the slide deck. But in R, when it wraps, it will give you the new index value, so you sort of know where you are in the vector. Nothing wrapped here, so we didn't get the index value, and it's even doing it when it returns these, answers to you. It's like, oh, this is the first entry in the vector. Now, which is, of course, now it should make all types of sense to you because we have vectors of length 1, right? In R considers everything vectors, so it doesn't see this as a doesn't see that as a scalar or whatnot. So it indexes as 1. Okay, we can do the same thing for the other variables. So family gender, male, female, da 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 da. And then it's got this thing after you print it, it says levels MF. So as soon as you get that levels information, that should tip you off that probably this is a factor variable. And when we look at the class, yes, indeed, it is actually classified as factor. So what's going on in the factor variables is they are common enough in statistical research that there's a special variable to represent this, a special type to represent this variable in R. And the type is factor. And when you see variables taking on the characteristics of, male, female, or lower, middle, upper, something like that, you can actually directly represent that as a factor, and R will store the information that represents the levels separately along with that factor. So that maybe doesn't seem particularly reasonable right now when we're looking at it, but when we get into applications and functions that actually use the factor variable, it can be a lot faster and more efficient to have that level information represented. And sometimes you have enough levels in a factor that and enough observations that you can't actually look at all the factors by, here we're just staring at all the data. If you can't do that, it's sometimes useful just to see how many levels there actually are and have it printed out right in front of you. So this is also useful for our information. Okay, family overweight is what's going on here. So we see these true falses for how each individual was classified. And when we ask what class that is, that comes out as logical, just as we would expect. So great. Okay, so the logical is true or false. The factor is special for qualitative data, as we just saw. And they are stored as levels, and the level is a character string. So you can actually query the levels itself. So levels, this should say F gender. It's actually will work as gender the way that data set is constructed, but just to be consistent with the previous slide, that should say F gender. And then it gives you the levels as MF, and it indicates to you with the quotes that these are stored as characters. They're not levels 1, 2, 3 or something like that. Okay. Special values in R, the missing value is NA, not available. NAs appear all over the place. You can have NAs that are characters and stored as characters, NAs that are numeric. So you can see here the fourth bullet, just seeing NA is different from the character string quote NA. And there are some handy sort of querying utilities in R, and is dot comes up for a particular query. So we can use that in this case, is.na. So how many missing values are there? Or are there missing values in this vector? Is.na fage, for example. We should get that there's no missing values, hopefully. You also see NaN, not a number, appear. Now that's different from a missing value. It means that it probably means your computation has gone awry. So if you've divided by 0, like by 0 by 0, like this, you get it's not a number. It can't actually parse this, so something's gone awry in your calculations somewhere. If you divide a non-zero number by 0, then it'll give you inf, of course, standing for infinity. And it's got minus inf in there if you happen to be, say you divided minus 12 by infinity. Null is an empty set, but the set exists. So that one's interesting when it means that there's no values have been entered into that set yet, but they could. Like R recognizes that the set is there. R is not actually smart enough to create variables on the fly. So if you call a variable that doesn't exist, R will give you an error. It doesn't kind of invent it, assuming that you meant to make it. And so the null is a little bit special in that it is saying it exists. It's just empty. So it's not like it's saying that there's nothing there and it doesn't know what's going on. So it's different to that. So here we say, are there any names associated with the values in family weight? And it says that's an empty set. It doesn't say the class of names doesn't exist. So the function names returning a character vector of the element names. Here there's no names, so we get that, that null. null response from R. Okay, so all sorts of ways we can query vectors. Length to find out how long the vector is. Head by default gives us the first 6 values. Names, as we just saw, if there are names associated, they would be listed. So here on f height, we have put in names A, B, C, just for an example. Is.na of f weight, false, 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 false. We don't happen to have missing values. Other functions that we can apply, min is f weight illogical, so we know weights are numeric, they're people's weights, so that one comes out as false. Is f height null? So is it a container that's empty? No, there's actual values in there. So as is a little different to is. Is querying a current status. As actually says, let's take the current status, whatever it is, and we'll try to force it to be something else. So as.numeric means take whatever function, argument to the function exists here, this vector, and force it to be numeric. So fgenders we saw was a factor variable, male, female. So we'd say force it to be numeric, and it will do a default assignment of numeric values to the factors. So it's m, f, m, m, and so on. And it just is 1, 2, 1, 1, 2, 2, and just represents them as numeric. So that if for some reason you need to enter numeric values into a function and you wanted to enter into a factor, then you can actually coerce it this way. So this is a little tip. Okay, so as we saw in the discussion of RStudio, we have a workspace in R that actually contains all the objects that are available for R to work with, maybe data you've read in or variables you've created, for example. You can see a list of them by typing objects like this into R. So R, if your function has no arguments, you still need to put the parens in there. Otherwise, it just thinks it's a variable. Right? If you just typed objects, it would be like objects variable doesn't exist. This in RStudio is the same thing as what's listed in the top right under the Workspace tab. So you can do it either way. If you want to get rid of things, RM deletes it. If you want to save a certain subset of that workspace, you can save it. Just give it a file name. You'll want to be conversant with where R is storing these things in your on your machine, like what the current local directory is set to. You can change that in the drop-down menu in RStudio. You can use commands in R to change it, but you don't want to just sort of save things and then you don't know where they went on your machine. You want to really have a lot of control over that. Similarly, when you load, you may need to put a directory path in here to load it, which is fine. You just want to know where it is. And then Q, paren, like I said, when you submit an empty function to R, you need to use those parens. Otherwise, R is not going to know to quit. If you just type Q, first time I ran, the predecessor to R, which is S, got stuck in there for like 20 minutes, couldn't figure out how to quit it because I didn't know that you had to have the parens in there. So that's how you quit Q, paren. Okay, subsetting. Subsetting, it sounds like a reasonably trivial concept. In some ways it is, but we're going to go through it in detail because a huge amount of what you do as a data scientist is subsetting. It doesn't sound very glamorous, but that's the reality of the situation, so you may as well get good at it. Okay, so there's many different ways to subset in R across vectors, and remember vectors are a canonical data type in R, so if we are good at subsetting in vectors, we're going to be good at subsetting in larger objects, which actually are just bundles of vectors in R. So we're going to work on vectors for now. So we took the family BMI data, and we wanted to take the 10th value out. That's called subsetting by position, and it will return the 10th value to you. And R, of course, is still indexing the return as 1, but that's the 10th value in the vector. Subset by exclusion, R will understand the negative sign, so we can take out everything except the first entry. Notice R is doing all of its subsetting, just like it's doing all its index calls with the square brackets. So the square brackets are how you're indexing. And so when we see square brackets used here, it's completely consistent to how it's used here and how we've seen it in the past because it's indexing. It's all indexing. Names, so if there happens to be name information, we can use that with quotes and characters to pull out the name. we can actually use a logical. So take all the truths that are in the overweight logical, and if the logical is true, pull out that corresponding entry in gender. So if there's an overweight flag, we can pull out male, female this way. Notice that it stays, whoops, it stays as a factor. We still are dragging around that levels information, which is really useful because this is MF, so it's coded as levels, so we want that information to come with us, and it does. Okay, we can similarly assign values to a vector. So we'll use some of those tricks that we just saw and make sure the vector is created, and then we can use our knowledge of indexing now to actually assign values. So let's see how that's done. So put in a particular index position where you would like the new assignment and just assign it. So the second value in f height will be written to 62. That would be this one right here. I mean, sorry, 61. It will be written to this one. You can say assign everything except the 13th value to be 62. So we'll go ahead and do that. The eth named one should be 67. It'll overwrite that one. Take all the truths in overweight, and anywhere the index matches for the index value for a true and overweight to f height, write that as an NA. If you say nothing here, what it means is make them all 70. So you just kind of say, write every single one as 70 here. So we'll get all of them. This last one is a bit dangerous because you haven't given any index information here. So what it does is it says, I'm going to set this variable f height equals to 70. Now remember last day, or in the last lecture, we saw that R will overwrite values without even thinking about it. So what's going to happen here is it will say, okay, you want a variable named f height equal to the scalar 70, or the vector of length 1, 70, and it will go ahead and just do that, and it won't say, are you sure you want to overwrite your other data f height? It will just overwrite it. So that's something to be careful about. Okay, so here's a sort of step-by-step of what happens. So make sure that you understand how to carry out each of these steps. I'll let you go through them. I won't go through them in detail, but it's just what we discussed on the last slide. Should be 2 slides of them. Yep. So we're just implementing our steps of doing that, the replacement of values. Okay, so we could get a little more complicated. So suppose we want the body mass index value for every second person in the family. It's a little bit of a weird query, but it's an example of taking these structured queries over data. You might want to do something like randomize or something like this over your data. There are reasons why you might want to subset in a more organized way. So we're going to do that. Suppose you'd like to take the weight variable but condition it on women in your gender variable. It's a very common type of thing to do in R and in data science, so that's a good one. Take out the heights where the name is A, C, or F. So you might want to look at particularly named observations. There's no last name in our family data set, so maybe we could create a variable that just assigns Smith to every single person in that data set, all 14 of them. So we would create an empty vector, assign all the elements to be Smith. Okay, so we need to know how to use logical operators to create logical vectors, and creating vectors with specific numbers or letters. We saw examples of these on the previous slide, things we might like to do. Okay, subsetting vectors. So here's our graphics of how subsetting works. If I say I want to subset on positions 1, 3, 7, and 8, I could list that vector and subset on that vector. So it will grab what we see here, 1, 3, 7, and 8. And then it gives it to you in the same order, 1, 3, 7, and 8, the same order that you requested it here in position, not necessarily the same order that it would appear in the underlying vector, the age vector. So if I requested 1873, that's, again, 73, but then 52, 67, 79, and notice that it comes out in the order that you requested it, 1873. So R thinks you're the boss, tries to do what you want, right? It's not sort of controlled necessarily by the indexing that was in the vector that you're querying. Okay, subsetting by exclusion, delete 2, delete 4, delete 5, delete 6, da, 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 da. Okay, so we can do this. We delete 2, 4, 6, da, 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 and then you end up with, 1, 3, whatever this is, 7, I guess, 8. And so that's what you get, 73, 79, 67, 52. So you have lots of options. Okay, you can use a logical vector like a filter, and it will filter data through it wherever the index value is true. So here we have true, false, true, false, 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 false. So these 4 t's that happen to be here will actually pick up these values, 73, 79, 67, 52, and they will actually filter through. So that's another way of doing it. You can use a logical to grab the values that you're interested in. Names. So notice that this graphical representation of the name information and how it travels with age. So that's exactly the way name works. If there aren't names in there, of course, then there could be. So as we saw, name sits there empty, so it's a null. And so we wouldn't bother, kind of writing it out there if it's empty. But names have, if they have values like A, B, C, they would travel alongside that vector, and you could use them for subsetting A, C, G, H if you needed them. You see those values come through. Notice names didn't come, that the attribute of names did not come through to the subsetted vector. So if you wanted to keep the names, you'd have to do that too. Okay, so what we've got, subsetting by position, subsetting by exclusion, subsetting by logical, subsetting by name, and we can actually keep or drop all the elements in the vector as we like. Okay, logical operations. We saw already, the sort of basic ones, plus, minus, and so on, operating as you would expect. And we can also use greater than, less than, greater than or equal to, less than or equal to. R uses the shriek for not, so this is not equals here. Different languages use different symbols. It happens to use the exclamation point. And then as we already saw, equivalence, so 2 equals will be equivalent here. All of them give true or false. So you're asking R to evaluate a relationship between 2 variables, so it's going to tell you whether the relationship holds or the relationship does not hold. And these operate over vectors, so they're actually quite fast in R. Is 4 less than 3? That's false. Is little a equivalent to big A? It's false. Remember, R is case sensitive. Is big A equal to big A? Yes. Is 4 not equal to 3? Yes. So little things like that. Okay, so we can apply that to vectors, right? It's vectorized. So we can say, is the vector f weight greater than 150? And it will do that by applying this logical relationship to each element in the vector. So the first one's over 150, second one's not, and so on. So it gives you an entire vector of trues or falses for whether or not this is true, or whether or not this holds. If f gender is not equal to m, we're going to get that false, true, false, false, and so on, depending on whether it's male or female. Let's take a look at the family BMI values. So you see them printed out here, 1, 25.16239, da, 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 right through to 6. You can see that's like 1, 2, 3, 4, 5, 6. So we are, again, indexing here is what R is trying to do. So it's trying to be helpful, even though actually I think it looks a little bit confusing, especially when you are first starting out in R. But what it's trying to do is be helpful and actually give you some indexing. Like, so we know that 26.05364 is the 11th value in the FBMI vector, for example. So what R actually displays to you on the screen may not be what it is, how the data are represented internally. So this is just something to keep in mind. So here R is defaulting as a printout to 5 decimal points. That's actually something you can customize and control in R if you would like. So what you could actually just ask it to only print 4 or print 6 or whatnot. So what's going on here I think is a little bit interesting. So we're asking in this sentence for R to tell us if any of the values, any of the entries in the vector FBMI are equivalent to 25.16239. Now, our I says that this is true, right? But what's going on here is that's just the representation that R is giving us on the screen. It's not giving us all the full decimal places that it has in its internal representation. So this comes out as false because, so 25.16239 is the same thing as 25.16239000000, and presumably this has more decimal places after it in the internal representation of the vector, and they don't happen to be 0. So this comes up as false. Okay, it's just this is a shortened version. What you actually see on the screen, there are actually more. So it's probably got like 3, 2, 1, 5, 7, whatever after it. Okay, so don't get fooled by stuff like that. Okay, so can we identify women in the family? F gender is equivalent to F. We can come up with a logical that way. And here's a very, very standard trick in R that you should definitely know. What we can do is use that logical vector to filter F weight, for example. And you don't need to calculate this logical vector in advance. You can do it in the indexing step. So here I am in between 2 square brackets. So we know this is indexing. We're asking for the creation of that logical vector, and we're going to just skim out all the female weights, 125, 105, 190, whatever. Okay, so that subsetting within the call to the vector, totally normal, totally useful. You'll use it a lot. So just make sure you really understand how to do that within the subsetting. Okay, so R does actually have an implementation of Boolean algebra. So Boolean algebra is going to essentially allow you to use things, operations such as not, or, and. And that can be hugely useful. A and B, not A or B, and so on. So it understands all of those operations. So a decision has to be made by any language that implements Boolean algebra around how it's going to understand or. Not is pretty straightforward. There's only really one way to understand that. Just the opposite of whatever is being called after not. And is pretty straightforward. You just sort of start additively putting pieces together of whatever is called. Or it's not always straightforward because you could have, like, so you consider the structure A or B. What happens if both A and B are true? Is the or true, or is it strictly one or the other? Which means that if A is true, then it would hold. If B is true, then it would hold. And if both are true, it would not hold. So you have to make a decision. So or chooses what's called the inclusive or. So if they're both true, it says the or is true. But not all languages do that. And that's the way that some languages use the exclusive or. So that's the way that R has solved that problem. And here you can see it. The compound statement A or B is true if either or both A or B is true. Okay, and then just a reminder here that the shriek, the exclamation point, is how not is written in R. Or is a pipe. If you haven't seen the pipe command, it's usually at the top right of your keyboard. You might have to do shift to get it. Top right, like shift top right, to get the pipe. Okay, so F weight greater than 150, if we put the not in front, it's like saying F weight less than 150. I want variables that are of F weight greater than 150 and F names are equal to Tom. It's only one. Oh, two, but get it here. Okay. F weight greater than 150 or F age greater than 65. Didn't see, we sort of get our variety of trues and falses coming out. So try these out. Grab the family data set, load it into our load family.rda, and you'll have all these variables available to you, and you can try exactly the things out that I'm talking about in class and that are on this slide deck. Just to keep in mind, things that are useful, any and all F age greater than 18, yes, they all happen to be true. Are any of them less than 18? No, none of them are less than 18. Are any of the weights less than 150? That's true. Are all of them less than 150? No. So you can see we're doing queries on the data using any and all that can be useful in particular settings. So how do we subset? We can subset, say, under 50. We can subset for women. We can subset for not overweight. We can subset for men who are 70 inches tall. Okay, so we've seen all these examples on the last few slides, so try them out. Make sure you're familiar with them. These are just so useful in data science. You spend a lot of time curating your data, subsetting your data, and so just knowing these tricks can really save you a lot of time and knowing how this works. Okay, so we can actually really do a lot more with logical expressions. So here, take all the ages of people who are not overweight. Get all the genders of all people who are aged over 50. Give me the BMI of the tallest member of the family. So I'm going to hit the BMI index vector, or BMI vector, with one value. It's going to be an index value from F height that's the max of F height. Okay, pretty slick, I think. So we're already getting into some pretty nice ways to use R. Okay, creating vectors. There are several different ways to create vectors. The most important one that you will definitely use frequently is C, and what that means is just put these values that are going to appear in these parens together into a vector. So concatenate vectors and values together. The colon says go from one value to the next by a step of one. We'll see some examples of this coming up. Seq stands for sequence, so we're going to create a little more complicated sequences. Repeat values in a vector. This can also be really useful. Sort works pretty intuitively, just sorting your values in a vector here. And ordering, provide the order of the values. So here we don't actually sort, we don't actually change that vector, but we work at the index level and we give the order of the indexing in the vector itself. Okay, so let's do some examples of this. C of 3, 2, 1, concatenate 3, 2, 1 together into a vector. All that happens is you see 3, 2, 1 here appearing in that vector. Concatenate 2, 3, 1, 2, 3, 1. So R is very respectful and tries to obey the order that you want and tries to create that vector that you want. Concatenate Bob equals 3, Alice equals 2, John equals 1. So how it understands that as names. So if you want to have names associated with the values, you could do it that way using concatenate or using concatenate. Okay, we can just type in caps true and caps false and create logicals. So here is a way of doing it. Concatenate true false, you get the true false vector. Concatenate 1.3 to 8 over 3, so it understands here your numerics. A, Z, hello. Now don't forget that vectors always have to be of one type, so you're going to have all your numerics, you're going to have your characters. Don't try to mix them up. R will just force them all to be characters if you do that. Concatenate is 100 and 120, and then we can actually put vectors of vectors together. So we defined X on the previous page. We just defined Y, stick them together, Bob, Alice, and John, and then you stick on 100 and 120. They don't have names, so that part's blank, but it can just shove them together like that, if that happens to be useful to you. Okay, so I said we would do a little bit more with the colon. So 1 colon 3, we're going to step up by 1. So go from 1 to 3, stepping by 1. 1, 2, 3. 4 to 7, stepping by 1. 4, 5, 6, 7. 10 to 6, it understands how to go backwards. 10, 9, 8, 7, 6. 1.1 to 5.7, it will try to do its best. It's still going to march up by 1. So it goes 1.1, 2.1, right up to 5.1. It has to stop at 5.7, so it never gets to 6.1. It stops at 5.1. If you do it in reverse, 5.7 down to 1.1, and it does the same thing. 5.7 to 4.7, gets to 1.7, can't go any further. Gets sort of blocked by 1.1. Don't worry about 0. R will float back past 0 either way. So 5.7 step by 1 to minus 1.1. You can see it goes 2.7, 1.7, 0.7, minus 0.3. It just keeps going. So that is a nice, easy thing to know, especially if you want to march along by steps of 1. Rep. So let's repeat the value of 3 2 times. Now, if you forget the order or what these functions or what these inputs actually mean, just do the trick that we learned in the last discussion, $rep, and you'll see the documentation and it will remind you of what to put here. You could also use another function that we'd seen previously, args. Args rep will tell you what actually goes in here. It will remind you. So we want 3, repeat 3 2 times. So let's make a little vector here, 7, 1, 3. We can repeat that vector twice. 7, 1, 3, 7, 1, 3. Can be really explicit and say times equals 2. Repeat the vector x times equals 2. 7, 1, 3, 7, 1, 3. We could even say, let's take that vector x, and now I'm going to repeat it concatenated times 3, 2, 1. So this is a little bit special because there are 3 values in x, 7, 1, and 3, and I'm telling R, this is of length 3 because I'm telling R how often to repeat each one. So repeat the 7 3 times, the 1 twice, the 3 once. 7, 7, 7, 1, 1, 3, 3. Each is really useful too. So we've got times and we've got each as arguments to rep. So put x in there. If x is a vector, repeat each element of the vector twice. 7, 7, 1, 1, 3, 3. Okay, rep, very useful. Seek is also very useful, standing for sequence. Has a little bit of a little richer set of options too, so we can see them if we just grab args seek or $seek. I highly recommend taking a look for both rep and seek at the help file. Sequence, go 1 to 5 by 2. So it'll try 1, 2 to 3, 3, 4 to 5. Okay, so for those of you that were thinking, yeah, I see the colon stepping us up by 1, but what if I want to step up by 2 or some other value? Seek is your friend to do that. You can ask it to do it by length as well, so go from 1 to 5 and create an output vector length of 3, 1, 3, 5. In this case, they happen to give the same output. Go from 1 to 5 and give an output vector length of 5. That's the same as 1 colon 5. It will figure out that it needs to step by 1. Start at 1. Make an output vector of length 3 and go up by 2. So you can do that and it's still not overdetermined. 1, 3, 5, 7, 9. Seek 1 to 5, length 5. So we know we can do this. We've got it up there. 1, 2, 3, 4, 5. And then forcing it to go up by 2 will cause an error. Can't, right? It wants to go up by 1 to satisfy this first part. So you've confused it. And then this is an example of how R doesn't always give particularly helpful error messages, but then you sort of start to parse them over time when you've seen a lot of them. So the first thing is it says it's an error. Okay, that's helpful. So error in seek.default. So this thing .default we see all the time. It's because this is the version of the seek function that's being used inside R. It's confusing the first time you see it, but just focus on this part because then it's relating to that implementation of that function. It gives you the commands here and it says, this is somewhat helpful, too many arguments. It doesn't say that your arguments are in conflict or why you have too many. You've got to sort of figure that out, but it's basically saying, I can't get what you want from the fact that you've given me 4 pieces of information here. Okay, so here are some ways you can kind of test out rep, seek, the colon, and the things that we've learned. So how can I type out 0, 0, 0, 0, 4, 6, 8? We know how to do this, right? So we put our 0 to 8 function in here using seek, and then repeat each element 5 times. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. We can rep 1 to 5 5 times, and it will repeat that entire vector 5 times. Repeat 1 to 5 times equals 5, so just like the above. And then if I add on repeating 0 to 4, each equals 5, I can get a pretty interesting I think it's a pretty interesting sequence. 1, 2, 3, 4, 5, and then the next chunk is 2, 3, 4, 5, 6. The next chunk is 3, 4, 5, 6, 7, and so on. And so we just did this by creatively adding them together like that. Okay, sort and order, ones that we talked about earlier. Sort, well, like I said, it luckily works in a fairly straightforward and intuitive way. It will sort from smallest to largest for your vector and return that sorted vector. You can control it with decreasing equals true if you want to sort from largest to smallest. Order just gives you the index. It doesn't actually change the order in the vector itself, but it will give you the index values for the sorted vector. So what it's saying is 12 is the smallest value, 5, the position 5 contains the second smallest value, 10th position contains the third smallest value, so that should be correct, right? That should be the 12th. 5, 1, 2, 3, 4, 5. Yeah, that's the next one. How did it do the tiebreaker? I don't know, actually, but it picked 12 and then it picked 5. 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Oh no, the 12th is the 24, and then this is the 27, and then 27 for 5, and then 10. Yeah, I don't know how a tie broke between them, maybe just order that it appeared in the vector. Okay, 12th element is the smallest, 5th is the second smallest, 3rd is the largest, and we can also do decreasing equals true if you want the reverse, and it would give you 3, 1, 7 for the largest. Okay, so for BMI of every other person in the family, remember that was one of the questions we wanted to answer. So now we have the tools to answer it. We can say for the index values that we want to extract from the BMI function, let's take the ones that are in a sequence 1 to 14 by 2. So now it seems kind of trivial to us. So try that one out. Weights of the women in our family, F gender equals female, is equivalent to female, applied to F weight. Height elements ACF, we can do that one now. We just put in that that catenation of AC and F. And then we've got one outstanding one. Assign everyone in the family the last name of Smith. Okay, there's a couple ways maybe you could do this, probably even more than the ones that I'm going to do in class. So we could set up this vector last name by having a character of length 40. So if we take a look at what it is, there's nothing in there, but there's 40 placeholders. And then we say, fill everything in last name with Smith. Then it goes ahead and does it. So that's one solution. Last name, L name, is an empty character. So if we look at it, it's null, right? Like it's empty, but it exists. Character of length 0. And then we would say, well, fill positions 1 to 14 in L name with Smith. Then it goes ahead and does it. So that's another way to solve the problem. Okay, data frame. So data frame is the core data object in R. And this, again, comes from this statistical thinking that our data set is of primary importance and in R. And for a data scientist, it is. Okay, so let's look at this family data set again, where we've got family, height, weight, first name, gender, all sorts of information. So the idea of a data frame is if you have related variables, then why don't we just group them all together into a data set? So we can coerce this data.frame, first name equals F name. So this will be, first name will be the value in the data frame, and the data will come from F names, for example. Gender, let's take the variable F gender. Age, we'll take the variable F age, and so on. So gather them all together. That's what it looks like. So you can kind of tell it's a data frame when you get an eye for this, because this index value down the left-hand side, which is not meaningful, right? It's not like this is the first column in the data frame. This is just the display in R, the same way it was indexing. It tries to index everything it returns. So it's just sort of helpful visually, but it's not actually in there, but it does tip you off that this is probably a data frame when you look at it. So family has first name, gender, age, height, weight, Tom, male, 77, and so on. So we've kind of grouped them all together into a coherent structure. So data frame, order container of vectors. So this is, first name, height, weight, so on. Vectors have to be the same length. So this is a severe restriction on the data frame. It doesn't work for all data sets. If you think about measuring patients or human subjects the way we are in the family data set, it makes some sense. They have to be the same length. So you can have missing data in there. There can be empty spots, but they all have to have vectors of the same length. Vectors can be different types. We could get name information as character, weight information is numeric, we have logicals in there, and so on. So they can certainly have different types. Let's take a look at what classes they are. A class of family is a data frame. Length is 7. Number of variables, not number of observations, so make sure you got that one. Dim gives you dimensions of family. 14 observations or rows, 7 variables or columns. And then names, so these are the variable names in the data frame. So that hopefully is somewhat intuitive. It will just give you the names of the variables. To access a variable in a data frame, R uses a $sign. So this is maybe a little bit, sort of throws you off when you first see it, but if I want to get the gender variable out of the data frame, I say my data frame is family and I want gender. And it gives it same as what we've seen with fgender. Mean of the height variable in the family data frame, 67.07. Class of the height variable is numeric in the family data frame. Subsetting data frame. So we can actually just take all of our knowledge from subsetting that we just built up and apply it to the data frame. Why not? We're just going to do it in 2 dimensions. So all our indexing previous to this was 1 dimension. We had basically 1 number in here or 1 set of values. Notice this comma in between, so now we have 2 sets of values in here, and it's for each dimension. So here we're going to subset 10 to 13, so 10, 11, 12, 13, 4 values. On the rows, on the columns, everything but 3 to 14, so basically the first 2. So that's what appears here, 10, 11, 12, 13 for the first dimension, and then we got first name and gender, the first 2 values for the second dimension over the columns. Okay, you can do all the same stuff we're used to, position, exclusion, logical, name, all, any, so on. Same subsetting, we just have it divided by this comma to go over both dimensions. So try this out. Get that family data set into R, create the data frame, and try and do this subset and see if you can end up with Tom, Ann, Dan, Art, all the rest. Okay, if it's blank, when we do the subsetting, that means take them all, just like we've seen when we did this at the vector level. So take all observations, and I want the concatenation of gender and first name, so those are the variables I'm interested in. So there we see it, and notice it comes out looking like a data frame, not like a series of values. So we can get really elaborate. We can say, take all the observations where weight is greater than 180, and take the variables height and BMI. So here's the answer. So we're using logicals and we're using names in there. Okay, so we can sort of, in a sense, if we want the output to have a certain format, the way we call it will allow it to preserve that format. So let me give you an example. So it's taking the family data frame and just asking for height like this, the height variable, will give us the height variable, but notice it preserves that data frame structure. If I say, give me all the observations that are in the variable height, this looks a lot like a vector, right? So you can actually get that vector output. So it is in fact the case. So the first one is a data frame, the next one is a numeric. Now you could use this extraction technique to pull out the height data. Then you could use what we had learned earlier and say as.numeric to force this to be a numeric vector, but it's probably just easier to just do it straight from the source as a numeric. So one of the things you're probably starting to notice is that you spend a lot of time with data representation in R, converting between, a data frame, a numeric to character, and so on, and it's true, and you do end up kind of doing those conversions a reasonable amount, for better or for worse. Okay, so I want you to know how to upload data into R. The old school, most traditional, most reliable function to do that is read.table. That's a very rich function, and it should probably be the first place you go when you try to read data into R. If you are reading in a CSV file, so these are comma-separated values, like typically what would come out of Excel, you could save your Excel work as a comma-separated value. There's a special function, read.csv, that just knows that it's CSV data coming in, and you can use that. You don't have to. Read.table can handle comma-separated values perfectly well. You just say sep as one of the arguments for separator is a comma, and it will do it just fine. So here we go, sep. Okay, so these are arguments: what file, if there's header information, sep, what do you do with missing values, are there any numbers of lines to skip at the beginning of the data that you're reading in. Those, you can see them all with question mark read.table or args read.table, just like we're starting to get familiar with. You can look at all those arguments. And then that's how to get pretty much any data set into R. So here's an example. So R is clever enough to be able to read URLs in there. So here's read.table, file equals, and I've got a URL here to a text file. Header information is true, so they have some kind of variable names or headers in their file. And then when I look at it, what's the dimensions of CA Quakes, the file I read in? 383 observations by 4 variables, so I hope that's right. You should always check that. That's like the first check. Make sure you've got the right dimensionality when you read in data. And you can take a peek. So what's the first 3 observations? All variables. And you see date, latitude, longitude, magnitude. Looks reasonable, right? That looks like latitude, looks like longitude, looks like magnitude information. Something that's a little weird is these dates are all kind of strung together. What's their class? They're integers. So one thing that we probably will, you'll almost always be spending time doing if you read data in, is you'll end up doing some kind of manipulation of the data to just make it easier to work with it. So having dates stored as integers, it seems like it loses some kind of structure and some information here. We know that's year, we know that's month, and we know that's day. So somehow I'd want actually that to be stored in R. Okay, but we'll come back to that. All right, so I said that data frames had to have every vector in the data frame the same length. This can be a limiting restriction for some types of data. So when it's a limiting restriction, you can actually use a list. Lists don't have that same restriction. So let's start from the ground up with lists. So if you create this list here, so if we're thinking about sandwiches, we could have 2 elements in the list that describe these sandwiches: what cheese was on the sandwich and what meat was on the sandwich. In this case, there were only 2 choices of cheese. There were 3 choices of meat. So this isn't going to work for a data frame. So we create the list. Cheese is concatenation of cheddar, Swiss, so characters. Meat, concatenation of ham, turkey, bologna, also all characters. So we have our ingredients list. And the way that it actually is displayed on the screen is it says $cheese contains cheddar and Swiss, $meat contains ham, turkey, bologna. Okay, that's fine. We don't have the same position information, the same vector information as we did before. We can pull out we can still use the $ indexing by name. We can use the square brackets to index like vectors. So let's see an example. There's just one little trick that I'm gonna build up to here. Okay, the second element in ingredients is the meat. So when you say 2 like this, because they're indexed differently, you're not gonna get like cheddar than turkey, like you would in a data frame. Instead, it pulls out meat for you. That's the second element as far as it's concerned. What class is this? It's a list. So this list contains lists. That's a very normal structure that you want to get used to. To go into that list now, you use 2 square brackets. So just be familiar with this terminology, try it out, and make sure you're comfortable with it. So if I go into ingredients, now we know 2 is meat, and I say, okay, dive into meat, but actually just give me the contents of meat is what that extra square bracket is saying. And so you get now a vector, ham, turkey, bologna, instead of the list. So notice these are classified as character. And then you can operate with them as a vector. So just know that with lists, there's that little extra structure on there. Okay, so lists are pretty common in R. R will like to return lists to you when you do operations because it can actually deliver extra information to you in the list structure that, that can sometimes be helpful to you that it wouldn't ordinarily in, say, a vector structure. So this example here is essentially just a sort of little quick observation on how it returns a list. So let's see here. Okay, so regression results. So here we just fit, you can sort of ignore the fact that we're fitting a very small linear regression model here. Don't worry about what exactly that means at the moment. But there's output from this function. The function to fit the linear regression model is LM, and then we're saving that in regression results. So the whole point of this example here is to say, look, that output is actually list format. If you look at names, it's giving you a whole bunch of stuff. Don't worry about what all these mean. But the output is not, it's not a number, it's not a vector, it's actually a list with a ton of information. Okay, so here's the graphic of the list. Notice a list could contain a data frame. We haven't talked about matrices yet, but a list could contain matrices, contain vectors, like this is what we saw with the ham cheese example. You can throw anything in the list and they don't have to be the same dimensions. Okay, so let's finish off with matrices and arrays. Just like you learned in math, matrices are a rectangular collection of elements. A matrix in R has 2 dimensions, so columns and rows. Arrays are higher dimensions, so you would have columns and rows indexed over time, for example, or space. So arrays are higher, just 3, 4, or 5 dimensional, and matrices are 2-dimensional. Every matrix or array, just like a vector, has to have all the same type in it. So they'll be all character or they'll be all numeric. Okay, so here's an example. So here we're building up matrices using the matrix function. So what this is saying to R is build a matrix for me using 1, 2, 3, 4, 5, 6 with 2 rows and 2 columns. Now notice R populates this column-wise, so different to how we would read it. So it goes 1, 2 down the first column, 3, 4 down the second column, 5, 6 down the third column. If you want to force it to be how we would read it, like going by rows first, you say by row equals true. Then you can see it populates 1, 2, 3, 4, 5, 6. It's up to you to do it, either way you like. You can actually assign names. This can be useful for display, useful for manipulation of the matrices. So you can say, label my columns ABC, label my rows AB. Notice a little trick here, letters gives you the alphabet. Dimensions gives you rows and columns. N row, number of rows, N col, number of columns. This will be useful for when you get to wanting to loop over values in a matrix. You might want to know the number of rows or the number of columns. T, a very simple little function, just transposes the matrix. Okay, so a matrix is actually just a vector decorated by index information for where the position of each value should be in the matrix. So that means you can use all of our subsetting information and all the skills and techniques we learned for manipulating vectors on a matrix. So you can use these same 5 methods of indexing. First index value goes over rows, second over columns, just like in math, so that's perfectly consistent. And whoops. Okay, so same with the data frame. We'll use a comma to delineate between an operation on a row and then an operation on a column. So here this is saying, give me everything except the first entry in the row, and then give me the second column. Okay, everything except the first row, I'm sorry, and the second column. And here, give me the row that's named A, and give me everything in the columns. Give me everything in the rows, and first column, second column, not the third column. Okay, try these out and see what you get. I mean, all of the steps are here in the slides for building that little matrix and giving it names, and then just try these commands. Okay, our summary. We've got vectors, data frames, list, matrices now as core data representation elements in R. As I mentioned, matrices and arrays are stored as vectors, and they are decorated by the index information or the shape information, so we can carry out all those vectorized operations on a matrix as well, which is super useful. Data frames and lists are not like that. So here's indexing our data structures. Just a quick summary. For vectors, we just have the index information between the square brackets. We're working on 1 dimension. So here are examples to try out. Data frames have 2 dimensions, so rows and then columns. So we get in there with our sort of our 2 dimensions here. So here, for example, all the rows, columns 3 to 4. We actually pull out variables with $ as well. So that's a way of getting into the columns here. So family $weight, pull out the weight column is what it's saying. And we can mix it up. Family $weight greater than 70, so all the observations where height is greater than 70, and all the columns. For lists, we can pull out list elements with $name. So remember, that's how we got ingredients $meat. We could do ingredients $cheese. We descended into the list using the square brackets to pull out the index, but remember that returned a list. And if we wanted to return a vector, we had to use the 2 square brackets that actually took that content information out of the list and returned it as a vector. So like you see, whoops, here. Matrices, they're indexed and accessed in a sort of standard way, so exactly as they are actually in mathematics when matrices are taught. Your row index and your column index. One thing that's helpful, if it might be helpful, is that we can also grab name information if it exists. Okay, $ and our double square brackets index only 1 element, so they're only going to pull out 1 column or 1 list of information in the list. You can't sort of grab 2 columns, for example. Okay, I am going to leave this here for this week. We are going to pick up again next week. I will put your homework out online today, and you will have that due next week. I'm going to be online very soon, actually. I'll try to get online for an interactive session. If worst comes to worst, just email me and I'll just sort of be rapidly answering emails over 4 to 5 today in my typical office hours, and successfully not getting you sick, at least not from me. All right, so I'll do that very soon, and I'll get this uploaded right away. Okay.